Hello students, welcome to Sir's classes. In this video, I will be solving some of the questions from ISS 2015 paper 2. Now here we are given a statement that a minimal sufficient statistic is always sufficient. So the statement is a minimal sufficient statistic is always sufficient, and we have to state whether this statement it is true or whether the statement is false. Now, from the definition of minimal sufficient statistic, we can say that a statistic T is called minimal sufficient statistic. Minimal sufficient statistic. So the statistic T, it will be called minimum sufficient statistic if it is sufficient. If it is sufficient and can be expressed as a function of any other sufficient statistic, and it can be expressed as a function. So it can be expressed as a function of any other sufficient statistic. So T, the statistic T, it is called minimal sufficient statistic if it is sufficient and can be expressed as a function of any other sufficient statistic. So by this definition we can say that the minimum sufficient statistic, so from this definition, we can say that the minimum sufficient statistic has to be sufficient statistic as well. So that is, if a statistic is minimal sufficient statistic, then it has to be sufficient statistic. That is, a minimal sufficient statistic is always sufficient. So our given statement, that is a minimum sufficient statistic is always a statistic, this statement is true. As we can say by this very definition that for being a minimal sufficient statistic, a statistic has to be sufficient. So a minimal sufficient statistic is always sufficient. Now in the next question we have to state the regularity conditions and then give the Cramer-Rao lower bound for the variance of an unbiased estimator of a parameter. Now here we make two regularity assumption on px theta. So we make two regularity assumptions on px theta as number one, that the set A, which is the set of X, where this P x comma theta, this is greater than 0. So for all these, so the set of all these X, it does not depend upon, so it does not depend on theta, and for all x which belongs to A and theta which belongs to, so our theta is belonging to this parameter space denoted as the following. So for all x belonging to A and theta belonging to the parameter space, we will have our d theta of log, so d theta of log of px theta. So this exists, that is d theta of log px theta, this exists and is finite. So this is the first regularity assumption, and the next regularity assumption is that if T is any statistic, if T is any statistic such that we have our Ex mod of T, this is less than infinity for all theta belonging to this parameter space, then the integration and differentiation by theta can be interchanged. So then the integration and differentiation so the integration and differentiation by theta, they can be interchanged. In integration of Tx into Px theta dx, that is, we can write this d theta of integration of Tx Px theta dx. This can be written as, or this is equals to, integration of Tx into differentiation with respect to theta, that is d theta of Px theta dx. So if T is any statistic such that Ex of mod of 3, it is less than infinity for all theta belonging to the given parameter space, then the integration and differentiation by theta, they can be interchanged, as we can see that d theta of integration of Tx into Px theta dx, this can be written as integration of Tx into d theta of Px theta into dx. So these are the two regularity assumptions on Px theta. And now this Cramer-Rao lower bound, I am writing it as CRLB. So this Cramer-Rao lower bound of variance, so the Cramer-Rao lower bound of the variance of the unbiased estimator theta cap, it is given by, so the variance of this theta cap x, this the lower bound of it, so it is given by, this is greater than equals to 1 divided by minus expectation of d square log p of x given theta divided by d theta square. So this is the Cramer-Rao lower bound of variance of the unbiased estimator theta cap. That is, the variance of theta cap, it is greater than equals to 1 divided by minus of expectation of d square log of px given theta divided by d theta square.